Audio recording for this meeting has begun.
So again, good afternoon, everybody, or good morning, depending on where you're located, and even welcome to our viewers who may be watching this recording. Today I'd like to introduce our four presenters today before I hand it over to them for some formal remarks. Today's topic is freeway incident detection and management using unmanned aircraft system. This is phase 2 of a research project. I'm going to read some brief introductions about our four presenters today before I hand it over to them. Our first presenter will be Yu Zhang. She is a professor in the Department of Civil and Environmental Engineering at the University of South Florida and leads the Smart Urban Mobility Laboratory at USF. Dr. Zhang develops mathematical programming and optimization solutions, simulation tools, uh, and statistical models and machine learning, deep learning methods for obtaining innovative solutions for a resilient, efficient, and sustainable multimodal transportation system. We have Miss Yvette Cruzado. She is a professor of civil engineering and surveying department at the University of Puerto Rico, Mayagüez. She teaches transportation engineering related courses. We have Dr. Achilles Cortales. He is a senior research associate at and assistant director of ITS, Traffic Operations and Safety Programs at the Center for Urban Transportation Research at the University of South Florida. He has conducted studies in evaluating safety-related technologies with data collection for rail transit, bus, large trucks, passenger vehicles, motorcycles, pedestrians, and bicycles. And then finally, we have Joseph Post, who is a visiting professor of practice in the Department of Civil and Environmental Engineering at the University of South Florida. He has a bachelor's degree in aeronautics and astronautics from MIT, a master's degree in engineering and applied science from Yale University, and a master's degree in economics from George Mason University. With that, I am now going to hand the presentation over to Yu Zhang. So I'm going to hand it off to you. Take it away.
Okay, great. Thank you so much, Stephanie, for the logistics and also for the introduction. So welcome, everybody. Good morning, good afternoon. And today we'll talk about the research that's sponsored by NICR. And we look into the freeway incident detection by using the Unmanned Aerial Systems. And I'll try to, okay. All right, so before I jump into the slides, I want to acknowledge other team members, including Hualong Tang and Kassiner Yachuri, and also Brian Porter. Those are the graduate students at USF. And also we have Brian and Ruth. Those are master students from University of Puerto Rico, Mayagüez. And also we have 3 faculty members from UPRM provided the comments and suggestions through the project. So today's presentation will include a brief introduction about this research, the motivation and also the scope of the research, etc. And then followed by the literature review. And after that, I will ask Mr. Post to talk about, the FAA regulations for UAV and also how we determine the data collection sites. And after that, Mr. Post will also briefly introduce one big component task that we have done in the phase 1, which is to compare the object detection algorithm with different setting parameters for the stationary RGB and the thermal sensors. And actually, University of Puerto Rico has done some parallel research on that, and Dr. Yvette will talk about that. And in phase 2, we focused on the incident detection. So we have done some data collection for both normal conditions and also under the incident conditions. And Achilles will talk about that. And after that, I will take over and introduce some of the progresses that we have made in developing incident detection algorithm. And we haven't finished this part totally yet. That's why we still have some work in progress. So NICR is a center focusing on the congestion reduction, and the congestion could come from, could include a recurrent congestion and non-recurrent congestion. And the countermeasures of alleviate recurrent and the non-recurrent congestion could be different. And for the non-recurrent congestions, incidence is a big kind of driving factor into that. And compared to other non-recurrent congestion, maybe caused by the work zone and others, actually congestion caused by the traffic incidents could be very random. And also the severity could be high. And also it could cause the secondary incident and it leads to more congestion. So currently, I think the detection of the incidents will rely on the road ranges and also the monitoring from the traffic management center. And however, there are more advanced technologies started to be considered and potentially be used in the incident detection. And also not only just the detecting, I think the incident clearance could be rely on some advanced technologies as well. So those are kind of the motivations for us to consider this project at the beginning. And I'm kind of, I trained for using operations research in aviation research. And I also always be very interested in emerging technologies. So we have done some studies using unmanned aircraft systems. And we have seen that, UAS actually have been used widely in different fields. And that's why we thought about, how we can apply the UAVs and also the sensors mounted on the UAVs to enhance the capabilities of monitoring and collecting the traffic data and extracting the features, and then to improve the incident detection and also the clearance. So here we list a kind of the scope of the phase 1 and the phase 2 of this project. And I want to say that the phases here are not the entire complete scope of our research. Some of you may have listened to the webcast done by Dr. Crucci from UPRM. So in the phase 1, actually one big task that UPRM finished is to develop a protocol of applying or using the UAV to collect the traffic data along the freeway. And Dr. Crucci has talked about that in the previous webcast. So in phase 1, the main efforts that from USF side is we did experimental design and look into the combination of different parameters while collecting data. And then we trained the object detection algorithm to see how the algorithms will perform given the data collecting with the different combinations of parameters. And then in phase 2, we focused on developing the learning model to detect the incidents. So here are some specific research questions we want to answer, and I will not read all of them. So it's kind of as I mentioned a little bit earlier, is that we looked into in the phase 1, look into how to design the experiments and how to evaluate the performance. So what could be the performance metrics that we want to use to do that? And in the second phase, we explored the state of art of incident detection algorithms, and also we looked into what could be the features that we need to extract from the traffic data collected from the sensor in motion, which means the sensors in the moving drone, and then what could be the efficient incident detection algorithms. And also it leads to the question is how the research outcomes can be used by stakeholders, including incident management personnel. And that's why actually through this project, we have been closely working with TNCs, both in Florida, District 7, as well as in Puerto Rico, San Juan. So I will go through the literature review very quickly. We looked into different areas. The first area is we did an overview about the applications of drones in transportation management. So the drones have been used in the incident detection, monitoring the highway traffic, and also provide additional information for the response team. And the UAV is also used to detect and analyze abnormal driving behavior from the safety perspective. And some researchers have used the UAVs to try to detect the trajectories of the vehicles and do more microscopic level research. And another area we looked into is to compare the RGB and the thermal cameras and images. This is because the existing TMCs, they monitor the traffic conditions with the cameras mounted somewhere on the pole or at the top of the building. But current TMC do not store the videos, and they do not use it for traffic management, considering a privacy issue. So there are specific guidelines from FHWA, from AASHTO, from the safety agencies about how to use those videos collected from the cameras installed on the freeway. So that's triggered our thoughts about how about the thermal images? Because thermal images actually hide a lot of the privacy information. And if we can test and prove that the thermal images can lead to similar detection performance, then probably we can go around these privacy issues. So that's why we looked into this area as well. And the next is we looked into the existing literatures on the vehicle detection algorithms. And we also looked into the references into the automatic incident detection algorithms. And we did the table to summarize our findings, and found out there are some pattern recognition-based approach or catastrophe theory-based approach to detect the incident, as well as using the statistical models, and rely on the AI, like machine learning, deep learning methods. And another group of references actually try to use the hybrid methods. So after this, I want to ask Mr. Joe Post to start to talk about the regulations of UAV and also the data collection sites.
Thanks, Dr. Zhang. I'll briefly explain why we conducted the drone experiments in the manner that we did. The Federal Aviation Administration regulates all civilian aircraft operations in the nation's airspace from the surface of the Earth upward to the edge of space. Commercial small UAS operations are governed by Part 107 of Title 14 of U.S. Code. While strictly speaking, we're not a commercial operation, we can't be considered a recreational operation. And although state, local, and tribal organizations needn't necessarily comply with all the aspects of Part 107, we would have needed to petition the FAA to operate outside 107, which would have required a letter from the University Systems General Counsel Office, and this would have taken a lot of time, and in the end, the FAA would have made us comply with most of the regulations anyway. So we decided the most expedient thing to do for this research was to operate under the Part 107 regulatory regime. So that implies many restrictions affecting our operations, including that the drone must weigh less than 55 pounds. That's not a problem. Pilot in command must hold an FAA-issued pilot certificate, remote pilot certificate. The drone cannot be operated from a moving vehicle. Visual line of sight must be maintained with the drone at all times. No operations over a human being. And this would include a moving vehicle. No operations in Class B, C, D airspace, so controlled airspace. We tried to avoid, we did avoid. And no operations higher than 400 feet above ground level. Now, any of these rules can be waived, but application must be made to the FAA, and in most cases, a risk analysis must be performed and risk mitigations implemented. Again, we elected to comply with the Part 107 rules to avoid the time-consuming process of applying for these waivers. So the implications for our experiments were then that all UAS operators required a Part 107 remote pilot certificate, which we did. All our remote pilot grad students obtained the certificate. The drone must remain below 400 feet. It cannot overfly the highway under observation. So we were always offset. Neither could we overfly entrance or exit ramps or crossing roads that might have traffic on them. The pilot in command had to maintain a visual line of sight, as I said, with the drone at all times, and operations must remain outside of the controlled airspace. So what does that mean? This is the FAA's VFR terminal area chart for the Tampa Bay area. And the blue lines, the bold blue lines here depict the Class B airspace surrounding Tampa International Airport right in the center. This central ring here is shows where the Class B airspace extends to the surface, which is essentially a no-fly zone then for us. The next ring here overlays the USF campus. The Class B airspace begins at 1,200 feet above the surface. So we could fly in that area. And we also had to remain clear of Class Delta and Charlie airports, towered airports, and these include things like St. Pete Clearwater International over here. Of course, Sarasota is down here, Lakeland over here, and a few others. Brooksville is up here. All right, so zooming in a bit, I've depicted the two imagery collection sites that we used to initially collect imagery along I-275, right here, yes, and I-75 up here. And I've also depicted the two incident sites where we collected imagery, again along I-275 over here, and I-75 over here. So these were all clear of controlled airspace. Okay, this figure depicts the drone geometry relative to the roadway and the test matrix used in phase 1 of the project, in which the drone remained stationary. You can see that we varied the height above the ground up to 400 feet, the azimuth angle of the camera relative to the roadway, and the depression angle relative to the roadway. We collected imagery using both the RGB or visual sensor on the drone and the infrared or thermal sensor. The performance metrics we used for evaluating the target detection algorithms are precision, recall, and the F1 score. These are standard metrics used in pattern recognition and information retrieval. Precision is the fraction of relevant detections divided by all detections, and recall is the fraction of relevant detections divided by the total number of vehicles present in the scene. In other words, it's probability of detection. F1 then combines the two into one metric in a harmonic mean. So Stephanie, you can hit the video now. Thank you. We found in phase 1 that the RGB sensor slightly outperformed the infrared sensor, as the background subtraction algorithm we were using could be confused by noise in the thermal imagery. However, the performance with infrared imagery could be improved by adjusting the algorithm's parameters, so further research would be required. Note that we did have a paper at the recent TRB annual meeting on the results of this first phase of the project. And with that, I will hand it over to Professor Cruzado. Take it away.
Thank you, Joseph. Good afternoon, everybody. I'm Yvette Cruzado from the University of Puerto Rico at Mayagüez. And very quickly, I want to tell you how we collaborate with USF on this project. So one of the things that we do is that we collect video data from our side to run the algorithm as well. And one of the reasons we do that is, well, one, because as you're going to see in the next slide, Puerto Rico's topography is very different from Florida. We also go a little bit beyond in our experiments, and we have a good relationship with the Department of Transportation in Puerto Rico, so we can have access to their data that they collect from other technologies, and we can do more comparisons. We follow a split plot design where we try different combinations of drone elevation and its distance from the road to evaluate the performance of the algorithm. Now, these are pictures taken from the beginning. This is where you can see how different Puerto Rico's terrain is from Florida. And we also like to show them because I believe this is the first time, we were not actually collecting data, but it was the first time we were on the field. And at that moment, there was a traffic incident. I think it was just a minor collision between two cars. But you can see how the line of cars are forming and expanding down the road. So before collecting the actual data on a freeway, we collected data at a test site in Hormigueros. So one of the things we checked if the camera angle in a drone will affect the performance of the algorithm. And by the way, the answer is no. And we also collected data at night just to check how the background subtraction algorithm will perform under these conditions. This is all preparing us to an actual experimental site, which is, we selected Caguas North Toll Plaza, mainly because right there are highway sensors and we can have access to that data. So what I wanted to show you in this picture is how important it is to check the combinations, that combination of elevation and distance from the road, because, for example, depending on that combination, sometimes passenger vehicles can hide behind tall vehicles like trucks, if you can see on the right side. And also one of the things that we noticed is that white cars traveling down the dynamic toll lanes, those are the two lanes in the middle, they will blend in with that background, with those two lanes. So to conclude, we manually count cars per frame, and we compare the number of those cars with the number of the cars detected by the algorithm. And that way we can determine which combination of elevation and distance from the road is better. Now, what we want to do also in the future is to compare the data that can provide the algorithm with the data that is given by the sensors from the Traffic Management Center in Caguas North Toll Plaza. And this concludes my part. I believe Dr. Achilles is next.
Thank you, Yvette. So I will go through the data collection we did during incidents, which basically means data collection during a live incident, either a crash, or in this case, it was actually not a crash, but it was an incident that happened on the highway that produced congestion. So the idea is that after phase one, we had to collect data while the drone is moving. This picture depicts how the drone is looking down on the highway. And of course, as Joe mentioned, the drone flies over the shoulder of the highway, so it's not over vehicles or people. And the view, in a nutshell, that's what it looks like. And of course, the drone is moving either left or right in parallel to the highway. So our first incident, actually, I should mention that we were lucky enough to have one of our graduate students being also a trainee at the local district FTOT district office here. So we partnered with the road rangers, and they were able to. He was able to ride with them. And of course, Road Rangers, it's a program in Florida where they help motorists either when there is an incident, a crash, a disabled vehicle, or whatever is the case. So of course, they see all kinds of events happen on the highway. The first incident here was recorded on I-75, which is one of the local highways here and close to the Salmon Expressway in Hillsborough County. And that's the location you can see here. It's actually the flight path of the drone, and basically so that he did not fly over the ramp. As Joe mentioned, we cannot fly over the ramp, so as you can see, it flew between the two highways in the median. So we use a combination of automated flight controls and manual to collect the data we want. And as you can see here, it was a large dump truck that overturned and spilled basically sand, dirt over the lanes. So as you can see here, you can actually see on the left the dump truck and tow trucks trying to make it straight. And the idea here is that we're trying to collect the video of the congestion that is happening due to this incident. So you can see it's a major highway of 4 lanes, and it's being reduced to 1 lane because of this incident here. The second incident we collected data for was on I-275, again in Tampa, a little bit north of Bears Avenue, towards kind of the edge of the city there. In this case, as you can see here, we show the congestion that happened because of the incident here, and this is the flight path of the drone. So again, we fly over basically dead space, so no vehicles are there or people. And in this case, it was actually a pickup truck with a trailer filled of concrete, and apparently lost control and overturned the concrete mixer and dumped concrete all over the place. So again, from 3 lanes and a ramp, there is a ramp there, we only had 1 lane that was working. So it created a big incident. The difference here was that it was during the middle of the day, so actually traffic was fairly light. But the idea is to collect video from here, going downstream the incident, so that we can basically collect data and use it for analysis and optimization of the algorithm later on. And I think I'm gonna hand it over to you.
Okay, great. Thanks. So continue on what Achilles has mentioned. So now we have the data both from the normal traffic condition as well as what happened during the incidents. So the next what I want to share with everybody is about how to develop the incident detection algorithms. So first of all, we using a deep learning model. We trained and developed the deep learning model to detect the vehicles. And with that information, we have a learning model that can help us extract the traffic flow features, including the density, the speed, like median speed, max speed, average speed, etc. And we also can calculate the standard deviation of the speed. And on top of that, we also look into how we can define the level of service of the roadway. And with that information, we generate the features that we can use to train our machine learning model. And then eventually we use that model to predict anomalies. So in phase 1, we actually look into the object detection algorithms, either with the stationary camera, we used this background subtraction, and also for the moving, we used the deep learning model. So here, just I think, Stephanie, there's a movie. Can you please show the movie, please?
It's playing.
Oh, okay, because I think I had the full screen. Let me go back. Yes, so you can see that in phase 1, when we look into a learning model using the public available parking lot data set, if we directly use that, we cannot detect any vehicles on the road. That's why we trained this model with our own data. And then here, Stephanie, if you can show the next video. So next couple of slides, I just show you the detection performance with the different settings of the parameters, the heights and also the degrees, that as what Joe has mentioned. And this slide shows the RGB images, and next slide shows the thermal images. Yeah, so as Joe mentioned, the performance has a slightly difference, but even with the thermal images, the performance could reach to like 90% accuracy. However, after we collected the traffic data during the incidents and we applied the same deep learning model, we found out that we couldn't detect some of the vehicles either at very low speed or stopped on the freeway. So you can see from this slide. And that's why we further improve the algorithm. One is we label more images, and also another one is we increase the resolution of the images to be used in the learning model. So there's some text that I will not read through. It just talk about, the reason for using the certain level of resolution but not higher, because that possibly could leading to the overfitting of the model. And after we improve the model, now we actually can detect all the vehicles, no matter if it's sitting on the lanes or if it's going with a very slow speed. So the next slide shows a flowchart of how to extract the traffic features that could be used by the learning model for detecting incidents. So we got the data, we got the information from the deep learning model, and then, as I mentioned, we use the sensor in motion, which means the drones are moving. So if we have that data, then we can actually look into the speed. So if drones is not moving, we directly apply the Lucas Canada optical flow trackers to detect the speed. And if not, then we get the ground speed and then combine that with the speed from the model, then obtain the vehicle speed. And once we get that all that information, we can come up with the density, the different statistics of the speed, and also the level of service. So for the level of service, this is a table from the highway capacity manual showing how we can determine the level of service dependent on the density. And then the density that we obtained from the deep learning is on the pixel per frame. So we use the method described in this lower part of the slide to convert that pixel per frame to the passenger vehicle per mile per lane. And then we can determine the level of service. So next slide, Stephanie, could you please show the movie? So here's the demo showing the results of the feature extraction. So you can see from this movie that we can we have the speed, we have the also the dense. I think the so we have the speed on different directions. We also have the level of service. C and F, those are shows the level of service. All right, so once we have all these features, our next step is to develop this learning model. And if you look at left side, so we will consider these variables in our learning model. The top part is about the density, median speed, maximum speed, and the standard deviation of the speed and level of service at the current time. And we also look into the difference of these variables at the current timestamp and the previous timestamp. And then with all this information will become the inputs for the SVM learning model. And then we will detect the anomalies from the normal condition. And we are keep on collecting more data on the incidents. Actually, Achilles mentioned, Brian Porter is the master students who are working with a road ranger to collect more data. And we will develop this algorithm and then detect the non-recurrent congestion caused by incident. And then with more data, we're also going to validate this model. And then ideally, we will have another phase of this project, and we will transfer this model to University of Puerto Rico. And given data that they collected from Puerto Rico, they can test that algorithm as well as validate the algorithm with the data collected from their side. And so that's why we have some work in progress that we are doing right now. One is that compare the performance of sensors in motion versus mounted sensors in existing transportation infrastructure. That has been mentioned by Dr. Yvette, and they are collaborating with the TNC in San Juan on this task. And another one is we're going to apply the algorithm of extracting the traffic feature to a larger set of images, uncongested, and also we will collect the data for the recurrent congestion and also non-recurrent congestion, mostly due to the incidents. And as I mentioned, we'll test the model, validate the model, and also test both from Florida side and Puerto Rico side. And in phase 3, we'll also work together with the Traffic Management Center, both in Florida and Puerto Rico, to see how the outcomes of our research project could be potentially implemented by their centers. So while we're doing this research, we actually already did the real-time detection. So we have the drones flying and collecting data, and meanwhile, we have the computers on the ground, and the data will transfer real time to the computer, and we run the algorithm in the computer, and then we can obtain the traffic features real time by doing that. So we also looked into how the data could be transmitted to a cloud server, and then we have the algorithm there that can detect the feature, abstract the features, and also to detect some of the like the number of the vehicles, the density, the speed, etc., etc. So I think that's all for today that our team will share with you. And thank you very much for your attention. And we welcome any comments and questions.
Thank you so much, you and everybody, for the great information and information on your webinar. The resources are also available, or the references are also available at the end of the PowerPoint presentation, which are available in the files or handout section of Adobe Connect. Simply click on the item you wish to download, and that will save directly to the computer. So what we're going to do now is we've got about 18 minutes or so for some questions. So what we'll do is you've got access to that Q&A box, which is located in the bottom right-hand corner of your screen. Let's start with the first question. It says, what is the heat signature for an electric vehicle, and does that complicate using the thermal approaches?
I can take that. So we have not investigated the difference between electric and regular vehicles yet. However, keep in mind that even electric vehicles, at least in what we have seen so far, because of the sun, obviously they have a certain, the outside of the car is certainly hot, so there is a difference between that and the road, and that's what we're detecting. But that's a good point that we can investigate further, just to make sure that we adequately collect the electric cars, which are obviously increasing day by day.
Okay, this question is for you. Dr. Zhang, did you get the speed and density directly from the pixel values, or would you want the first detect vehicles and then get the speed and density values from the vehicle positions? And why did you select one approach over the other?
Okay, thank you very much for the question. Actually, what we have done, by going through the phase 1 and phase 2, is that we first detect the vehicles, and then given the position of the vehicles, we get the speed and density. But eventually, actually, we combine everything into one algorithm, which means once we get the images, we can do the detection of the vehicles and then speed and densities all together. So the demo that you have shown, in the flow chart, I kind of separate the different, steps, but for the demo that you have seen, everything has been combined. So yeah, I think both approaches could work. It's just it's the nature of our research, just going from one step to the other. So that's why we kind of chose the second approach.
Okay, thank you. Joe, this question is for you. I'm going to sort of ask this in a two-part question. Have you considered tethered drones that may not require Part 107 license for remote pilots?
Yeah, we did not, and I think that the reason for this is we were envisioning a future where the regulations are. The regulations continue to evolve. In fact, even during our project, they changed in some regards, like operating at night and operating over people. So they continue to evolve, and we're envisioning a future where it will be possible, where they'll be relieved further, and it will be possible to fly the drones further. And therefore, we were interested in actual mobile platform that could cover more highway than, say, a tethered drone, which is akin to a fixed camera on a pole. So that's why we didn't consider.
So
tethered.
I'll ask. Okay, I'll ask the second part of the question how do you go about obtaining the remote pilot in command license for operating drones?
Well, it depends. If you do not have a regular pilot certificate issued under Part 61 of Title 14, then you have to take a test. So you study, and there are lots of resources available, and then you take a test at a FAA testing center and score a high enough grade, and you're issued the certificate. But it doesn't require sign off from a flight instructor or anything like that. If you have a Part 61 certificate, such as I did, then it's really easy. You just need a flight instructor to give you the approval.
Okay, this question, there's three parts to this question. Once this research is completed, can you discuss how this might be applied in practice? Do you believe that UAS have advantages over fixed monitoring cameras? And have you gotten any interest from state or local DOTs yet?
I think I can start answering these questions, and then other presenters may add on. So currently during our project, we have already been collaborating with the TMC's Traffic Management Center, both in Florida and in Puerto Rico. And as I mentioned, we're gonna get into the phase 3, and in phase 3, we will mostly a large percentage of our effort will focus on the implementation. What are the barriers and how to suppress those barriers, and then look into the use cases. And I mean, we believe, or at least I believe, that UAS have some advantages as a sensor in motion. One is it has a flexibility of going to different locations, and also the drones that we are using have the dual cameras mounted, and then they can collect both RGB and the thermal image. So on one side, I mentioned earlier, is it can suppress the privacy issue, and could be more accepted by the public for being used in the traffic management. Another thing is the fixed traffic monitoring camera may could cover the entire freeway, but with a different resolutions dependent on how far the particular site is away from the camera. And also in the US, we have some roads with no monitoring camera installed. And I think the UAVs could provide a supplementary monitoring resources to those areas. And another thing is, I was thinking in the future. So we talked a lot about the drone delivery, like the small parcels could be delivered by the drones. And some discussion talked about the delivered drones actually go along the road network. And if that's the case, it's possible to obtain some of the information from those drones if they have like RGB cameras installed, and then they could become the sensor in motion without the significant capital investment from the public sector. But of course, that's something in the future, and we don't know how that would be in the future. So the last question is, got any interest yet from state and local DOTs? So when we started this project, or even before, even before we get this support from NICR, actually we have already talked to the FDOT about, using drones to getting the traffic data, and also, use that for the traffic management. But back at the time, the attitude of legislation and also the other public sectors were not so positive. However, during all these years, we have seen the acceptance and interest from the public sectors have changed a lot. And so actually, we mentioned that Brian Porter is he's an employee of FDOT District 7 office, and he obtained the pilot in command, remote pilot in command through this project, and then he has been asked to provide services for different offices in FDOT, like from the survey offices, from the structure offices, from the traffic engineering, etc., etc. So yes, so there are a lot of interests from the state and local DOTs. And I think Yvette can echo that, because we had a summit in Puerto Rico in last December, and we met with high-level officials in transition sector there, and he's very interested in implementing the drone technologies in traffic monitoring, traffic data collection, and incident detection. So I'll stop here, and if other presenters have something to add on, please feel free.
No, I think you said it all. I mean, from Puerto Rico's part, they are very interested in applying this, and there's a lot of segments in the freeways that are not covered by sensors. So the drone technology, I mean, it could, how do you say this? Like it could cover so much more area, and you can move it from place to place. So yes.
Yeah, I think the bottom line is it would be more, we think it would be more cost effective to cover a large amount of area.
And then there was just a sort of a, go ahead,
Sorry,
I do apologize.
No problem. Just to add on that, sorry, I didn't mention, is when we were talking to the traffic management center personnel, they also mentioned they want to get more detailed information before organizing the incident clearance, and then they believe that the drone with the sensors mounted actually could help on that, and it can go to the specific incident sites and collect the images with the detailed information, so that can transmit the information back to the traffic management center, back to the emergent responses team, and then they can have a better ideas about what needs to be dispatched to that particular incident site. Yeah.
And then there was just a follow-up comment to kind of go with that was, I think that the idea to identify TMC use cases is a great idea. You might also consider the TMC pooled fund study group as another opportunity.
Mm-hmm. Thank you.
Okay. There was a question here that needed some contact information. We'll follow up with you via email after today's webinar. So we won't respond to that question in the live setting, but we will get you an answer after today's webinar. Achilles, this question is for you. What are the challenges that you have encountered in data collection?
Well, at this time, as we already mentioned a few times, there are certain limitations in flying drones. One big one being that we cannot fly over humans or moving vehicles with some restrictions. Clearly, those rules, as Joe mentioned, are being relaxed, meaning if you do certain things, you can fly over vehicles. So basically, those didn't allow us to fly over the roads, so therefore it kind of limits where we can fly, or if we have a ramp entering or exiting the highway, we have to make sure that we don't fly over it. So that kind of at this time anyway limits where you can fly. That's really the biggest. And then the second one that we were able to, the second challenge that we had that we were able to actually overcome was being being informed of an incident and be able to record it live so we can get that footage and train the model. But we were lucky enough to be able to have this opportunity to ride with the road rangers that see several incidents a day, and therefore be able to collect that information as it's happening, so that we can train the model as the best as we can, and therefore in the future when the drone is flying, say by itself, really down the road, or if there is an operation where several drones, a swarm can actually fly, and then it can identify incidents, by itself. The whole point is to train the model as best as we can with the most current data. So those are the two big things that, at this time.
If I can add to that, for at least for our part, I would say that one of our challenges is that we're planning a flight, and we have to check the weather because, we're going to go, let's say, Wednesday at 4 o'clock in the afternoon. The weather looks perfect. And then we go over there, everything is set up, and suddenly it starts to rain, so we have to cancel. I mean, I know it's a minor challenge, but that will certainly affect our agenda or our time schedule.
Thank you, but actually I completely forgot the weather, but obviously, as we all know, we cannot fly in the rain at this time anyway. So that's definitely something that in the future, either drones will be able to fly in the rain. And I think we are seeing some newer ones. They can fly in light rain at this time. But again, this is all just limitations on the technology at this time. The research is about exploring what is possible and eventually, having the tools ready so that when we do have the tools to do that, we can apply them and get successful results. Yeah.
Okay. Thank you, Joe, Achilles, and Yvette for the great presentation. I'm going to open up the evaluation for today's session. I do want to give you a few minutes back for your afternoon if you do need to get some lunch or take a break. So I have opened up the evaluation. Please take a few moments to complete that evaluation, as the feedback provided is not only important to the NICR webcast series, but as well as our presenters today. So that has opened for each of you. As a quick reminder, we do have another webinar scheduled for next month on June 16th, Travel and the New Normal. That registration is not currently open, but as long as you subscribe to our upcoming, subscribe to our newsletter, or like us on Facebook or connect with us on LinkedIn, you'll be the first to know about registration being open. So on behalf of the National Institute for Congestion Reduction, thank you so much for attending today's session, and we'll see you all next month. Bye, everybody.